Good evening, everyone. Today we'll be introducing data versioning. The agenda for today will be an introduction of the assignments, the tools we used for data versioning, and the summary. The purpose of this assignment is to experience different data versioning tools and compare the metrics using dirty and clean dataset on the same baseline model.
I'll quickly take us through our EDA process, and starting with our data set, we have this other classification data set here, and through our analysis, we've identified that the important features here are the alpha and delta, which are basically longitude and latitude, the photometric letters, UGRIZ, and each letter here designates a section of light of the electromagnetic spectrum, as well as redshift. Basically anything related to an ID column is dropped to prevent overfitting, but this is the data set we'll use in the analysis. Here we just explore the distributions, so we plot all the histograms. Important thing to point out is the class variable, which is our target variable in this analysis. There's three different possible outcomes. There's star, galaxy, and quasi-stellar object. And the other takeaway was we applied min-max scaling to the photometric letters, so UGRIZ received scaling. Other than that, these are our distributions. Here we plotted some of the correlations for the variables. There's not too much to take away here, but just part of the EDA due diligence process. I guess it might be worth pointing out that class and redshift were positive and moderately correlated, but apart that, just exploring correlations here.
Hello everyone, I'm going to introduce one of the data versioning tool we use called Neptune. By following the instruction, I was able to create a project in related to our assignment called data versioning. So this is the dashboard showing all the runs I have by updating and changing the dataset and giving me different metrics. The primary platform I use to integrate with Neptune is through Jupyter Notebook. There are just some pre-steps I need to do in order to install Neptune and log in the token and API in order to connect to the Neptune package. So I log my API token as run, and then it will start to track my update and my changes to the dataset, enable me to log any metrics to the Neptune data versioning. I load and store the dataset and log the clean dataset to the run for this version, and did some EDA following by importing necessary packages in order to run the artificial neural network and splitting the data. The baseline model we built for this assignment is through a neural network by building a couple layers. And the metrics we look at throughout all the runs is on accuracy and then time used. I firstly run through the model on a dirty data set and then on a clean data set, just to compare if there will be differences on accuracy and time used. And I need to call run stop in order to have the background job stop and shut down. Let's see what happens on the data versioning interface on Neptune. So the dashboard looks very neat, and this is the first time I ran, and this is the second time. As you can see, the accuracy were successfully recorded, and the time used is recorded as well.
So the other data versioning tool that we decided to use was Git large file storage alongside with GitHub. I found this a lot easier to use than the platforms that required Docker. All that was needed here was a little bit of Git command line knowledge. The Git LFS page has good documentation to follow, so it was relatively straightforward. There's a functionality in GitHub where you can see the data version along with a label at each step in the process. So we can see in the box at the top right that I uploaded dirty data, and then the version underneath it, I uploaded the clean data, and it's labeled there. And that's useful functionality, but it doesn't have the same functionality as Neptune, where you can see the data version and the corresponding model results, which make it probably a weaker tool than Neptune. However, the size of your files can be greatly increased, but we didn't need that for this. So after our EDA process and data versioning, we finally plugged both the dirty data and the clean data into the model. And understandably, the model performed much better when it had clean data as opposed to dirty data on the prediction, about almost a 40% increase in accuracy. And the specifications of the feed-forward neural network we used are listed at the bottom there.
Thank you, Henry. Now let's talk about differential privacy. Differential privacy is a promise made to a data subject ensuring that their data used in a study or experiment will not affect them in a negative way or rather at all. The goal of differential privacy is not that we can learn about an individual subject, but rather we can use an individual subject's information to learn about an entire population of people. In regards to differential privacy, what data are we ensuring to be private? This sort of private data includes personal identifiable information, sensitive information, and quasi-identifying data. Personal identifiable information includes contact information such as name, address, and phone number. Sensitive information can include financial information or healthcare information. The healthcare information could be things that align with HIPAA laws. Quasi-identifying data includes unique identification data such as credit card transactions and location tracking. The neural network. In the model architecture, we utilize the DP-Keras SGQ optimizer as the optimizer and the categorical cross-entropy as the loss function. Differential privacy is extremely important, yet there still is an impact when creating machine learning models. With our model building, it did require quite a bit of algorithm modification in order to achieve the correct model architecture for proper differential privacy scoring. Also, with the implementation of differential privacy using TensorFlow, once you increase the hyperparameters a lot, such as the noise multiplier, there can be accuracy trade-offs in which the higher the noise multiplier, for example, there could be lower accuracy values.
Just to walk you through the steps and script we wrote for DP computation. The first part is some installations on TensorFlow privacy package. And we define a parameter for optimizer and loss function. We built the baseline model. And we compile the model with the optimizer loss and indicate the metrics equal to accuracy. And as you can see, this is all the accuracy we got from the baseline model. Last but not least, we used compute DPSGD privacy functions to yield the values of epsilon and delta. Here is the comparison table on all the tools that we use in terms of the ease of installations, the ease of data versioning process, and the ease of switching. We rated out of 5 for each tool on different at different sections. And as you can see, Neptune stand out of all tools that we use to be the most convenient and efficient data versioning tool. Thank you for listening, and please feel free to ask any question.